Okay, I'm going to take a look at sections 3 through 5. The first one is specific heats. And typically we look at a couple of specific heats. One is when we have a constant volume, and one is when we have a constant pressure. Okay. And what is specific heat? Basically the amount of energy required to raise a unit mass a degree C. Okay. Couple of examples over here. Well, of course, if the substance is different, we would expect specific heat to be different. Okay, and here it is. Here's some examples: specific heat with constant volume, specific heat with constant pressure for helium. And one of the things that we need to take note here is that we have specific heat for constant volume, we actually get work. Work is not constant volume, constant pressure. We're actually performing boundary work, so we're going to find that this is more related to like the enthalpy of a system, change in internal energy, and the pressure times volume. Okay, or the boundary work. All right. Okay, continuing on with this idea. So in this case, we're looking at specific heat of substance with change in temperature. Okay. Just some notes. Specific heat of a substance changes with temperature. You'll find that usually it's not very big, but there is some variation to it. Okay. One question you can think about, is it specific heat with constant pressure always greater than specific heat with constant volume? Okay, and you can think about what you would expect for that. Okay, of course, CV and CP are properties, and CV is related to change in internal energy, and CP is related to changes in enthalpy, right? Because in this case, you actually have some work being performed, right? Okay. Okay, so here's the units. So this is like change, and this one is, are these units identical? And you can think about that, right? Well, it's really more of a relative measure, right? In this case, when you're talking about, if you're talking to a very specific temperature, right, these would be different. But if you think about it, a degree C and a degree K are essentially the same thing. Okay. Okay, and then this is talking about change in internal energy, temperature, constant volume, and representing it as like a partial derivative. You could represent it this way or this way, change in enthalpy. Okay, looking at section 4-4, internal energy, enthalpy, and specific heat of ideal gases. Okay, so through some experimentation, James Prescott Joule showed that the internal energy of an ideal gas is really just a function of the temperature. And from ideal gases, what we had found out before, that it's just the pressure times specific volume is equal to the ideal gas constant times temperature. Okay, using that in addition to our definition for enthalpy, the internal energy plus the pressure times our specific volume, the enthalpy can just be related to, or is just equal to, the internal energy plus the ideal gas constant times temperature. Okay, so with this result in mind, from what Joule had done, is that we now have internal energy as a function of temperature, and then of course the other component of the enthalpy is also a function of temperature for ideal gases. We also have which would result in the enthalpy being a function of temperature. Okay, and so from previously what we had looked at for, if we were looking for the incremental change in internal energy, it would just be, by definition, the specific heat for specific related to for constant volume is a function of temperature times delta T, and same thing with the incremental change with the enthalpy. It's just going to be equal to the specific heat at a constant pressure as a function of T times delta T. Okay. Well, if we're looking for change in internal energy and change in enthalpy, we can actually just use, we can integrate this term between our two limits or between our two states, and we can determine what that change is. And then the change in enthalpy also is just going to be the differences between the two enthalpies in those two states. Okay. And this is really, for ideal gases, this is what has been defined. They're all a function of temperature. Okay. All right. Continuing on. Okay, so for low pressures, we actually have specific heats defined for that. We have specific heat for constant pressure when it's low, or they call them zero pressure specific heats, and specific heat for constant volume when the pressure is low. And here's some plots for different gases. We have, CO2, H2O for this one. And there's actually, I'll bring this up, but on this table, there's actually some equations you can use to determine what the specific heat is. So if we pull up the table A2C, you can actually perform the calculations. They give you different values of for A, B, and C, and you can actually go through and perform the calculation. And they define it for specific temperature ranges, okay? Like I said, this is A2C for ideal gases, okay? Okay, and then, you can use this information, perform the integrations, and you can actually build a table from that for different temperatures for T, and you can come up with the the energy, internal energy, and the enthalpy at those points. Okay, so okay. So as I said, you could calculate these, and you can use 0 degrees as a reference temperature. Okay, we'll take a look at simplifying that in the next slide. All right. Okay. So for small temperature intervals, what we could do is we could actually consider it to be like a linear relationship between the two. Okay. So with that in mind, we make our calculations a lot easier then. Then we would just have for, change in internal energy is just going to be, essentially it's just delta U, right? Change in internal energy is just going to be, the average CV and the average CP, depending upon if you're looking for enthalpy here. And then it's just the difference in the temperatures, okay? So that makes the calculations a bit easier, and it's a very good approximation for that, okay? And what we'll find from that is that this is a good approximation. Whether or not it's a constant volume or not, we could use this, even if it's a constant pressure, okay? We can make that approximation for small t, delta T. So we can look at, different ways of calculating the delta U, or change in internal energy, or the change in enthalpy. We can use data that's already been tabulated, okay? And as long as we have those tables. The second way we could do it is actually going through and performing the calculations or the integrations. That could come to be very time consuming, because you'd have that little incremental change. You'd have to have a function to represent it. Or in this case, you just start with an average between the points. So you come up with an average specific heat and use that, okay? So these are kind of the three different ways. We'll look at some examples, and here's the where you could use the table for that. Here it is for the integration, and here is for using the average. Okay, so this works out pretty well for a calculation. All right, so either table, performing the actual integration, which is time consuming, or going through and numerically performing the integrations, or just using an average, okay, times the delta T, the CV average, or the specific heat at a constant volume average. Okay, so we could also look at, specific heat relations with ideal gases. And what we'll find is that the relationship between, CP and CV and R is just this, CV plus this ideal gas constant for CP. And then if we look, this is for if we're talking about like per mass, and this is if we're talking about it as a molar basis. So in this case, they do it as per kilomole. And we have this other term that we use, or a ratio that we'll find useful. And that's just going to be CP over CV, okay? And the ratio actually comes up to a few things. They can talk about if it's a monatomic or a diatomic gas. And which, essentially you're saying if it's monatomic has one atom, and if it's diatomic has two, okay? So for an example here, you can actually determine the CP or specific heat constant pressure just from these two, adding these two together, and the same thing at the molar level. Okay. Okay, so if we use this idea and we take a look at an example, heat of a gas in a tank by stirring. So energy in minus energy out equals the change in energy. Okay. Now, what we notice here is this, of course, is a constant volume case, okay? So there's no, the shaft work by itself is just going to be equal to whatever change in internal energy here, okay? Since there's no boundary work being done. So this, of course, we could just write it in terms of like the mass times the change in internal, the mass times the changes in internal energy is essentially just equal to mass times the specific heat average between those two temperatures. So essentially, what we had previously looked at. So, and it should make sense from the respect that, work went in, this is like a perfect insulator or whatever. So there's no like heat being lost through this. And what we could say is essentially that it's just going to be the mass times specific heat and the two temperatures, okay? Or the change in temperature. Okay. Okay, now we look at another example. In this case, there's work coming in, there's heat leaving, so it's not like a perfect insulator, and there's boundary work being done at the output, okay? So the change in internal energy is just going to be these, the differences between them, right? So it's like whatever comes in minus essentially whatever's going out is going to be the change in internal energy, okay? And then if we just take and essentially add the boundary work to the other side of the equation, now we have the change in enthalpy, okay? Which is just going to be the mass times the two changes in enthalpy per unit mass, since they're in lower case. And then it's just going to be the mass times, the mass times the specific heat, constant pressure, times the difference between those two temperatures, okay, or the delta T. All right, and here's what it looks like graphically, okay? And that was one of the main points here, right? It was a constant pressure. Okay, so the last example is a little different. Now we have a little bit different process path. In this case, we add heat energy into the system, and you follow this path until it gets to be up to, we get up to a certain pressure. Then all of a sudden now, the pressure increases enough where you are going to actually cause the piston to move up. Okay, so it's like sitting right now at this point, it's just sitting on these two points on the sides, or supports on the sides. And then, so this process goes up to 2, then it goes from 2 to 3, okay? And if we look at the equation, of course, it's just going to be, Qn minus the boundary work out, and that's just going to give us the change in internal energy. It's like heat in. That's the only how we're getting heat is coming in through the outer surfaces of the cylinder, and then minus whatever boundary work we put out. So the change in internal energy is just going to be, the difference between these two, which is just mass times the internal energy per unit mass. Okay. Okay, going to look at section 4-5, internal energy, enthalpy, and specific heats of solids and liquids. Okay. Okay, solids and liquids basically being incompressible, and what we're going to find is like the volumes remain constant during a process. Okay, and so what we're going to find in this case, of course, is that the specific heat for constant volume and constant pressure is the same, so we're just going to have a specific heat defined for those solids and liquids. Okay, so starting with our initial equation for change in internal energy per unit mass, it's just a change in from in whatever initial internal energy subtracted from the final internal energy. Of course, as before, we can just solve it by performing the integration. And what we found is that a good estimate of that is just saying that it's the specific heat average between the two temperatures is just equal to specific heat average times the change in the delta T, or the change in temperature. Okay. And now we can look at enthalpy, and there's enthalpy per unit mass. And using differentiation, we could write in this form, right? Because these two are functions. So we just have our specific, not specific volume, our change in volume per unit mass times dP plus our pressure times dV. Okay. And what we're going to recognize here is that there's no change in volume, so this term just goes to 0, and we're left with just delta U plus V dP. Okay, so this is like our sort of our end result here. All right, and then if we write it in terms of like our averages, or delta H, if we write it delta H instead of as in differential form, or delta H, or change in enthalpy per unit mass, is just going to be equal to delta U plus V delta P. Okay, which of course we can rewrite it just using what we previously had, is just going to be for our change in internal energy per unit mass, and then we just have C average, a specific heat average, times delta T plus V times our delta P pressure. Okay, and one of the things we're going to find here is that for solids, this is going to be insignificant. So then when we're dealing with solids, then just we're going to have just delta H equals delta U. Okay, so change in enthalpy per unit mass is the same as the change in energy per unit mass. Okay, and we have a couple of variations to this we need to think about. And if we have constant pressure processes, then it's just going to be delta H delta U. And then in the other case, if we have a constant temperature process, and it's like as in pumps, no change in temperature. So with that in mind, no change in temperature, of course, then this internal energy is not going to change, and we're just going to be left with our specific volume times that change in pressure. Okay, and then we can represent this, enthalpy at some temperature, pressure, at a specific pressure and a specific temperature, and just being like our then looking at the for enthalpy of a compressed liquid, then we can say it's approximate equal enthalpy saturated liquid at some temperature plus the same thing with the specific volume at some temperature, and then we have whatever pressure minus the saturation at that temperature. Okay, so this is a little bit better. A little bit better than, saying the enthalpy at some pressure and temperature equal just the saturated enthalpy at that saturated liquid temperature at some temperature, saturated liquid at some temperature, that enthalpy. Okay, so an example of cooling off an iron block by water. So same old equation, we're looking for change in internal energy. We have E in minus E out. Well, in this case, there's no change in internal energy. We're going to have, what's going to happen here. Maybe this thing is perfectly insulated. We have water, certain mass of water, and we have an iron block or a hunk of iron, I guess, of a certain mass being dropped in. So, and this is at a certain temperature, and this is at a certain temperature, and this is defined as we could figure out what the mass is because we have the volume. Okay. So in this case, we have a certain temperature, T1, we have some mass, we have C, specific heat of the iron, and we have over here, we have specific heat of the water. And we're trying to look at and figure out what the final temperature would be. Okay. So here's our equation. Here's our delta change in energy of the system, which of course we know is going to be 0. So we have change in internal energy of the iron plus the change in internal energy of the water. So it's like whatever energy will just be exchanged to the water. That total is going to be equal to 0. So we list out the equation for iron and for water. And what we'll find is, this is our T1 of iron, and this is, of course, T1 of water, is that we can actually go through and solve and figure out what the final temperature of the water is going to be. Okay, so that's this particular problem, trying to solve for T2. Okay, so that's pretty much it. There's some examples to go through, but we have moving boundary work, we looked at that for isothermal process, for constant pressure process, for polytropic process. We looked at energy balance for constant pressure or compression process. We looked at the specific heats, and then internal energy and specific heats of ideal gases. Okay. And we also looked at it for when we had incompressible substances, which was the last part. Okay. So now it's a matter of taking a look at some examples. Okay. And that's about it for chapter 4.